Hello, welcome to a video on the IMC inductive sensors. This is a deep dive into using our IO-Link master and SOPAS software into a PC to look at the different things you can do with this sensor, such as multiple outputs, so at different distances and different ranges, or picking up the difference between different types of metals, having window modes, changing hysteresis. So the more advanced setup for this sensor. If you don't know what the sensor is yet or are looking for just a simple way of using it, we have another video that just goes over how to take it out of the box and plug it in and actually start using it right away. So if you haven't seen that yet, go check that out. This is now the deep dive of connecting it to a computer and all the different things and the things you can squeeze out of the sensor. And it's not so much what this sensor can do, but it's what you can do with this sensor. So let's go check it out. So what we've got here is we have our IMC sensor just in a really simple stand connected to the SI-Link box, which is like a one-port IO-Link master. And then that's going into my computer and I'm running SOPAS. If you need more help on that, find other videos that I have on the channel. And here's the sensor. We're talking to it live. I'm going to take a piece of metal here. This is a zinc plated steel. And as I bring the target closer to the sensor on the screen here, I will see that I am able to now view and see the dampening of the inductive field that's being created inside the sensor. With this, as you can see, I can measure distance. So we can get distance out of it. So if you wanted to trigger an output, but you also wanted to get more information about how far away is that target for maybe condition monitoring to make sure things don't collide or hit anything. All right, so we are in our home setting. We can see the process data for IO-Link. Now, real quick, you can use this with IO-Link on your machine. You need an IO-Link master. You plug it in and really you'll get all of the information and you can set your switch points in your PLC. SOPAS and the SOPAS device driver make it really easy and visual. You can see graphs and things like that. Now, I'm going to grab my piece of metal. I'm just going to bring the target up closer and we're going to see here these bits change. As Q1 turns on, I get closer. Q3 is turning on. Let's dive into this a little bit more to see what we're looking at. I'm going to go into the detection tab. Now we can really see what's happening here. This is what we were looking at before. As I bring the target closer, which I'm doing right now, I get within the Q1 range. The gray is the hysteresis. The line is the switching output. As soon as I drop below that line, my output goes high. Now go take a look at the top. Qint1 went high and it stays high until I leave that hysteresis area. Once I leave that switching hysteresis, it turns off. So it goes on once I get closer to the target and it turns off once I leave the hysteresis. If I get closer and closer and closer, there's my Qint2. There's my Q3, switching output 3. And as I get really, really close, there's Q4. And we see here there's a larger hysteresis on 4, so I have to get all the way out of that big gray area in order for the output to turn off. And I'll go back up, meaning I'm getting further away from the sensor, so I'm lowering my target. And there we are. So at the bottom right, we see distance. We have to say right away, bottom right here and up here, we have these distance. They're digits. They're probably unitless numbers. It's not millimeters, it's not meters, because we don't know what metal you have. Now, you could calibrate this in your PLC. You could say, all right, I'm always looking for the same nut or bolt as like a homing position coming by. I'm looking for a metal arm. I'm looking for a metal plate. You can hook this up and say at 12 millimeters, I'm getting these digits, this number. But it's a way that the system, that the PLC and SOPAS here has to have in terms of how much field dampening it has and then being able to graph it. So it has to turn it into a number. And that's what those digits are, that distance is. Now, in your application, if you always have the same metal, same thickness, the same size, same material type, you can measure distance and you can get some condition monitoring information out of that. Or If you change metals, but you always have the same distance, you can actually determine different metals. So at the same distance, depending on the digits, depending on the output, the dampening that's happening, you can determine, oh, that was an aluminum, or nope, that was steel. So let's dig into this a little bit more. What is in the kind of the top right, the detection setup? So out of the box, and I'll just show you here, this is how you reset to factory defaults, which I already did at the beginning of this. Very good thing to always do, because as you're making some of these changes, who knows what you have. So basically that's how you get back to the beginning. Out of the box, it's set for 12 millimeter switch point and a 10 millimeter switch point on 2 of our outputs. If that works for you, that's great. I'm just going to turn off 2 of them right now. I'm going to turn off 3 and 4, just for the sake of making this easy to see. And I can move my switch points. And so now I have to get closer and closer and closer and closer in order for output 1 to turn on. And now output 2. I can actually type in digits because you might have to change due to the reduction factors of different metals. But I can also move this to where I want in space in my target. So I'm moving it between the 2 and I'm hitting the teach in button. Now I don't have to know the distance. I don't have to type anything in. I can actually just move my machine to the position I want it to be for different spots and just hit the teach button. I'm doing it manually here, but you can also send that command over IO link through and using the IODD files in your IO link master. So I can teach one here. Let's say I'll teach switch point 2 down here. Great. All right. What's this next one? Mode. And there's a little I next to a lot of these, which is really great. It gives you a lot of information about what's going on here. We'll come back to this. But the single point teach, or a window mode, 2-point teach, or the visual installation aid. Let's do single point mode. That is, I would say, a typical switching output mode. Anything closer than that distance, you get an output. So you see these outputs stay on as long as I'm closer than those top distances. All right, so let's take a look at the hysteresis. But the reason for a hysteresis is it helps us to not get a jittery output. So as I get closer and closer and closer, I don't turn on yet. I don't turn on until I get closer than the top point. Now, if I start to get further away right there as I leave that line, my output is still staying constant. I have to get all the way out of this hysteresis area before it turns off. And that just keeps things from jittering. So I set up now a hysteresis of 1000, quite a bit bigger. So now as I bring my target closer, it won't turn on until I get closer than the set point. Now my output turns on, and as I go out, it won't turn off until I leave the hysteresis. So I can bounce around in here and nothing happens to my output. We can also go into window mode. If I move the window, this is where things change. So I'm going to move my window settings here like this. All right. So now I'm going to bring my target back in. I'm going to bring it closer. Now the output will turn on and it will stay on, but now it turns off. And that's what's different. I'm now closer to the sensor and my output is off. A really cool, I don't want to call it a trick. I have 2 windows and I have Q1 here and Q2, and they overlap. This overlapping part is, let's say, where good is. So the correct thickness of the material you want, the right distance that you want. And if things move around in here, it says, yep, this is good. This is my go, no-go gauging. Everything's fine. If I get too far from the sensor, only Q1 is on. If I get too close to the sensor, only Q2 is on. Very cool, neat technique with one sensor, basically getting a go, no-go gauging. And this actually can work not just for inductive sensors, but you can do this with laser distance measurement sensors, ultrasonic sensors, anything that has multiple outputs and windows. I'm going to reset back to factory defaults again, just so you start over. So that way, if you're taking one out and you're starting from scratch, you don't want to go through all of the settings, you'll know where we're at. Now I'm going to go into this 2-point mode. And what this is really doing in this case is it's setting up your switch points and your switching hysteresis. So if I go to a spot I'm interested in here and I hit teach in on the first one, and then I move back away and I hit teach in here, I've basically set my switch point and my release point. Like it's the same as hysteresis. If you notice, there's no drop down for hysteresis here because it's basically like a single point teach as I turn on when I get closer than this distance, and then I turn off. All right, I'm going to reset back to factory defaults again. I've muted these other channels. I want to know the last one here, visual installation aid. In a lot of applications, your target is a engine block. It's your table. It's the sensor that you move when you mount it. So you use the nuts on here and you get it closer and you lock it down. That's what the visual installation aid on this IMC is doing. We also have it on the IMB, the IMM, and the IMX. So as I get closer to the target and I get to the range I want to be in, the light starts flashing. So there's the yellow light and a blue light indicating the two outputs. So the blue light's turning on saying, yeah, my Q2, my second output is on. But Q1 here is flashing, saying that I am in the proper detection range. Knowing where to set up your sensor, the distance to the target, is very particular. Inductive sensors using the coil and an oscillating inductive field, it's susceptible to temperature and other conditions, and as well as the metal and the eddy currents that are made. So there's a max range where the sensor can start to detect these eddy currents and get that dampening, but it may not be the quote safe range. So in the data sheets, you'll see potentially two different ranges, like a total max range and then the safe range that includes all of the conditions that might change in order to give you a very safe, reliable setup. We use these installation aids to let the installer know how you keep pushing it in until the lights start to flash. Then you lock down the nuts, and you know at that point you're as far away from the target as you can be, but yet be in a safe range. And again, safe, we're not talking yellow safety stuff here, but to be in a robust range that through any temperature cycles and changes, you will get consistently good outputs. And that's what the visual installation aid is on these sensors that have them. Out of the detection area, now we're going to move into the logic area. So I'm actually going to back up one more time. In detection, QInt, that's internal. So in a lot of smart sensors, what we're doing with it is changing what the bits are doing. So as I get closer to a range and I get to its triggering range, internally, I'm just flipping a bit. I have to now decide what I want to do with that. The most standard default way is you take your Q internal bit that says, yep, I saw a target closer than the range I taught, and I don't want to do any logic to it. No and or XORs, nothing. I don't want to have a timer. I don't want to invert the signal. I just want to have that go to my output. So here I'm going to take my metal target, bring it close to the sensor, QL, Q logic turned on, and I'm going to drive that right to pin 4, the black wire. I can now do that for the second one. So I'm going to say, oh, I want this to be QInt2. I also don't want to and this or here. Let's just do direct for now. But yeah, you know what? We can have a time delay. I can do a, I don't know, a 1 second time delay, something like that. And now it's just stopped here. So logically, if I'm in IO link, I can look at what happens here as I teach it. And I don't remember how I taught it, but I bring in the target in, Q1 goes on, Q2 goes on. But just the logical bits, bit 0, bit 1. Because my second pin, I only have 4, power, ground, Q1. This is going to my input. Well, I don't want it to go to my input. So I want this to be switching signal 2. So now I have my internal 4 options coming direct through here. The one's got a little delay on it. Why not? And now it flips bits for IO link and just goes straight to pin 2. Inverter is where you turn this into, let's say, a normally open to a normally closed sensor. No matter what happens on the output wire, these bits and this logic is always going high when the condition we taught it has been satisfied. It is in the logic area here that we decide, do we want that wire to go high or low? And that's it for this really cool sensor. Two switching outputs can be set up. Great for reducing the number of sensors. Great for determining distances to different metals. Great for determining different kinds of metals. Really neat sensor that can do lots of very cool things. So for more information on other things about it, check out the other videos in the links, and we'll see you next time.